this is, I believe, the 6th video on convergence and divergence tests for series, but it's officially the first video in part 3 of the different notes that we've been taking. So I think we have a total of 4 different tests that we've learned at this point to use for determining convergence and divergence. So today we are going to look at 3 more, and that will complete our options for determining convergence and divergence. So we're going to start today with the alternating series test. So alternating is going to happen when you have a series that truly alternates between a positive term to a negative term, to a positive term to a negative term. So it does have to alternate in that way. It can't be like one term's positive, then the next 3 are negative, and then the next one's positive. It literally has to go back and forth, back and forth, back and forth from term to term to be considered an alternating series. Those are also extremely easy to recognize in their summation notation like this, because they will have a negative number, usually a -1, raised to the nth power or the n plus 1th power or n plus 2, or a negative number raised to an nth power of some type. Those are going to alternate. And if you're ever not sure if they're going to alternate, write out a couple terms and see that they go back from positive to negative like that. They don't have to start with positive, but they do have to alternate back and forth. So if you have an alternating series like that, then there are 3 conditions that if you can prove that they are all true, then that will mean that your original alternating series converges. So notice here we have an a sub n expression and we have a b sub n expression. B sub n in all of these is essentially the absolute value of a sub n. So this is a lot like the absolute value theorem from sequences in the last unit. So we basically extract the portion of the a sub n formula that makes it alternate between negative and positive by removing that negative number to an exponent portion, and we focus on the remainder of the expression. That becomes our b sub n expression. If that b sub n expression meets these 3 requirements, then our a sub n series will converge. So the first requirement is that all the terms in the b sub n expression have to be greater than or equal to 0. So if you write out term to term to term to term for the b sub n, they all have to be positive numbers bigger than 0, which they should be if you've extracted that -1 to the n portion. Then the next thing you would need to show is that limit as n goes to infinity for b sub n has to equal 0. So you do the limit as n goes to infinity for that expression, and you get 0. If you don't get 0, then the alternating series test is false, and we know our series diverges. So that's the second thing we show, is that the limit is 0. And then third thing is that if your b sub n expression is a decreasing sequence, so the terms have to go down in value from term to term, then if all 3 of those bullets are true, a sub n, or the sum from n equals k to infinity of a sub n, converges using the alternating series test. So again, I like the alternating series test because it's really easy to decide when it needs to be used, and then it's just a matter of remembering the 3 bullet points that have to be met in order for it to prove convergence. So let's look at an example of where we could apply the alternating series test. So I immediately notice over here, I see that -1 to the exponent. Oh, this guy's going to alternate. And if you don't believe me, write out some terms starting with n equals 1. So we would end up with -1 squared, so that would be a +1 over 1. Then for our next term, we would have -1 to the 3rd, so that would be a negative number, over 2, so -1/2. And then we would have +1/3, and then -1/4, and so on and so forth. So that does alternate, positive, negative, positive, negative. So then what I want to do is I want to eliminate that portion of my expression. Well, if the -1 to the power is gone, all I'm left with in the numerator is a 1. So b sub n is 1 over n. Now remember, that's the harmonic series. It diverges, but I really don't care about that. I don't care that that guy diverges. It doesn't mean that the alternating form of it would diverge as well. All I want to show for that 1 over n is that b sub n is greater than or equal to 0 for all n. And in fact, all I have to do is state that. I don't have to write out any terms to prove it. I just need to look at that and realize, okay, my terms would be 1 over 1, 1 over 2, 1 over 3, 1 over 4, using that b sub n expression. Those are all greater than or equal to 0. So first bullet is met. Then the next thing I would need to do is I would need to find the limit as n goes to infinity for my b sub n expression, and that is 0. My second bullet point has been met. So then the third thing I want to do is I want to say b sub n is a decreasing sequence. And it may not be a bad idea to write out some terms just so that you have a point of reference to knowing in particular that first and that third bullet are actually true. Okay? So now that we've stated the 3 bullets and I can tell that they're all true, I would say therefore the sum from n equals 1 to infinity for negative 1 to the n plus 1 over n converges by the alternating series test. All right, so that's not too bad, as long as you can remember what the 3 conditions are. So it might not be a bad idea to make yourself a note card with the conditions. In fact, it may not be a bad idea to make yourself note cards of all the different tests so that you can remember them. Now, if you do have an alternating series and you determine that it converges, we actually have 2 types of convergence for alternating series. We have conditional convergence and we have absolute convergence. So absolute convergence means that not only does our a sub n series converge, but the absolute value of it, or the b sub n series that we were looking at, also converges. So we would say a sub n converges absolutely in that situation. An example of that would be negative 1 to the n over n squared. That's going to converge. And in addition to that, the absolute value of it, which would be 1 over n squared, also converges. So we would say that it converges absolutely. Now, if your a sub n, the alternating series, converges, but the absolute value of it, the b sub n, diverges, then we say that our a sub n series converges conditionally. So it only converges when it's in its alternating form. So an example of that would be the one that we just looked at, the negative 1 to the n plus 1 over n. It converged, but 1 over n diverged like we talked about. So usually if it's an alternating series, they'll say determine if the series converges, and then they'll say if it does, determine if it converges absolutely or conditionally. So you'd have to take it one step farther with that. So for example, we already looked back at the last problem, so we're good. Determine if the series converges absolutely, conditionally, or if it diverges. So here, I noticed because of that negative inside of what's being raised to the exponent, this would be an alternating series. And in fact, I could write out some terms here, and I would get so on and so forth like that. So I would notice that it alternates, okay? So then the absolute value of it, my b sub n series, would be positive 1/2 to the n plus 1. So the first question we ask ourselves is, are those terms for b sub n greater than or equal to 0 for all n? And if you're not sure, start with the same n value we start with here. So if I start with n equals 1, that would be 1/2 to the 2, which is 1/4. And then 1/2 to the 3 is 1/8. and then 1/16. The same terms as what I have above, except they don't alternate. And notice they are all bigger than 0. The next thing we do then is the limit as n goes to infinity for b sub n. So that would be the limit as n goes to infinity for 1/2 to the n plus 1. Now, that 1 being raised to the infinity plus 1, that's still just going to give me a 1 down here, or in the numerator. But then 2 to the infinity plus 1 would give me infinity in the denominator, which gives me an overall value of 0, like I need. And then the third thing is this a decreasing sequence? Well, if you look back at what we wrote out for b sub n, it's 1/4, 1/8, 1/16. So that does, in fact, decrease. So I write out my third bullet point. So now we know at this point that it converges, but the next thing we need to decide is it conditional convergence or absolute convergence? So that means we have to look at b sub n just by itself to determine whether or not it would be a convergent series. Well, the sum from n equals 1 to infinity of the b sub n sequence, that's geometric, because notice how my n is in my exponent. And if I wanted to find r, you don't realize that it's 1/2. You could do your second term divided by your first term, and you get 1/2 that way, which is less than 1. So therefore, this series would converge by the ratio test. So the final thing that we could say therefore, the sum from n equals 1 to infinity of -1/2 to the n plus 1 converges absolutely by the alternating series test. So I'm going to stop the video at this point now that we're done with the alternating series test. And the second video will cover the remainder of the test, the integral test and the p-series test for our convergence and divergence tests.